On an ordinary day, deep within a Google research lab, a machine named Willow was given an impossible task: simulate the behavior of materials at a molecular level. A problem that would take the world's fastest supercomputer billions of years. The engineers set Willow to work, its core chilled to near absolute zero. In just 36 seconds, Willow delivered the answer. This was not just a leap in speed, it was a paradigm shift. Quantum computing had arrived. The Willow moment became the quantum equivalent of the first flight at Kitty Hawk, proving these machines were no longer theoretical. The world of classical computing, built on zeros and ones, had met its successor. Suddenly, governments, corporations, and researchers realized quantum computers could reshape industries, medicine, finance, security, and AI. The problem Willow solved opened doors to new drugs, efficient batteries, and deeper understanding of the universe. Willow demonstrated quantum supremacy, a quantum computer solving a task no classical machine could in a human lifetime. For decades, this milestone was a distant dream. Willow crossed that line in seconds. Now the world faced a new question. If quantum computers can solve the impossible, what else is within reach? The race to answer that question had officially begun. To grasp Willow's revolution, we must understand the difference between classical and quantum computers. Classical computers use bits, zeros, or ones, like tiny switches. Every app, every video is just a long string of these. This binary system built the digital age, but it has limits. Quantum computers use qubits. Thanks to superposition, a qubit can be 0, 1, or both at once. Imagine a spinning coin. While in the air, it's both heads and tails. Only when it lands does it pick a side. A qubit exists in this in-between state, holding vast information. This is why quantum computers are so powerful. 3 bits can represent one of 8 combinations. 3 qubits can represent all 8 at once. With just 300 qubits, a quantum computer could hold more states than atoms in the universe. This isn't just speed, it's a new way of thinking, exploring countless possibilities simultaneously. Imagine a maze. A classical computer tries every path, one by one. A quantum computer explores all paths at once. It can see the entire landscape and find the solution almost instantly. This is the quantum leap, from step-by-step processing to parallel exploration of reality. The future of computation is no longer linear, it's exponential. If superposition is quantum computing's first pillar, entanglement is the second, what Einstein called spooky action at a distance. Imagine 2 spinning quantum coins, entangled. Flip one in London, and instantly, the other in Tokyo reveals the opposite. This connection binds qubits together, letting them work in perfect harmony. Entangled qubits form a single, complex quantum state, each qubit's fate linked to the others. This creates a computational web where changing one qubit influences the whole system. Classical computers compare data point by point. Entangled systems see the whole picture at once. Think of a symphony. Classical computers play notes in sequence. Quantum computers play in perfect harmony, all at once. This collective behavior lets quantum computers tackle problems with complex relationships, like simulating molecules. Entanglement isn't just weird, it's essential. Quantum algorithms use it to create shortcuts, solving problems in a fraction of the time. The more qubits you entangle, the more powerful your quantum computer becomes. Superposition and entanglement together form the foundation of the quantum revolution. It's a partnership between the weirdest and most powerful ideas in physics. This is what makes quantum computing truly transformative. The Willow moment ignited a global race for quantum supremacy. Nations now see quantum computing as a strategic asset for economic and national security. The US, China, the EU, and others are investing billions, each vying to build the first large-scale, fault-tolerant quantum computer. The race isn't just about the number of qubits, but their quality, stability, and control matter just as much. Quantum error correction has become a game changer, making logical qubits more robust and reliable. This progress is moving us from noisy, error-prone machines to the dawn of fault-tolerant quantum computing. The competition is fueling rapid innovation, not just in hardware, but in algorithms, software, and talent. More funding leads to better machines, which enable new discoveries, attracting even more investment. The global sprint is pushing science and engineering to new heights. The next breakthrough is always just around the corner. Quantum computing's impact on medicine will be profound. Drug discovery today is slow and expensive, relying on trial and error. The human body is a complex chemical system, and simulating drug interactions is beyond classical computers. Quantum computers, operating on the same principles as molecules, can simulate these interactions with perfect accuracy. Researchers could design new medicines atom by atom, targeting diseases like Alzheimer's and cancer far more efficiently. Quantum simulations could also unlock personalized medicine, tailoring treatments to an individual's unique biology. Understanding protein folding, a key to many diseases, becomes possible. Early quantum computers are already tackling small-scale simulations, paving the way for future breakthroughs. The promise: a new era of predictive, personalized, and powerful medicine. Quantum computers will revolutionize materials science. The properties of materials, strength, conductivity, are determined by quantum interactions. Designing new materials has been slow and imprecise, but quantum simulation changes that. Imagine creating catalysts to fight climate change, or room temperature superconductors for lossless energy transmission. Quantum computers can model atoms precisely, enabling custom-designed materials for any application. The same power applies to optimization, finding the best solution among countless options. Quantum algorithms like QAOA can solve logistics, finance, and manufacturing problems far more efficiently. Hyper-efficient supply chains, new financial models, and optimized manufacturing become possible. The economic impact could be staggering, unlocking trillions in value. AI and machine learning are hitting the limits of classical computation. Training advanced AI models requires massive resources and energy. Quantum machine learning, QML, fuses quantum power with AI, enabling new ways to process information. Quantum computers can analyze data in high-dimensional spaces, spotting patterns invisible to classical AI. They could supercharge AI training, finding optimal solutions faster and enabling larger, more powerful models. This could accelerate breakthroughs in medicine, science, and beyond. Researchers are developing quantum algorithms for machine learning, hinting at exponential speedups. The future may see hybrid, classical quantum AI, combining the best of both worlds. Our digital world relies on cryptography, codes that protect everything from bank accounts to state secrets. Classical encryption is based on problems that are hard for today's computers, like factoring large numbers. But Shor's algorithm showed that a powerful quantum computer could break these codes in moments. This threat, the quantum apocalypse, has sparked a race for quantum-safe cryptography. New codes resisted to both classical and quantum attacks. At the same time, quantum physics offers unbreakable communication through quantum key distribution, QKD. QKD uses quantum principles to detect any eavesdropping, guaranteeing perfect security. This isn't just theory. QKD is already being deployed in high-security networks. The quantum era will transform both the sword and shield of cybersecurity. Building quantum computers is one of humanity's toughest engineering challenges. The same quantum properties that give them power also make them fragile. Decoherence, loss of quantum state, can be triggered by the slightest disturbance. Qubits must be kept in ultra-cold isolated environments using massive dilution refrigerators. Scaling up is hard. More qubits mean more complexity and more chances for error. Quantum error correction helps, but it requires hundreds of physical qubits for each stable, logical qubit. To build useful machines, we may need millions of high-quality qubits, a goal still far off. Quantum computers aren't universally faster. They excel at specific problems. New algorithms designed for quantum mechanics are essential. Without the right software, even the best hardware is useless. Overcoming decoherence, scaling, errors, and algorithm development is the central challenge. The global quantum effort is focused on solving these interconnected problems. The path is difficult, but the rewards are immense. The journey to practical quantum computers will take decades. In the next 5 years, we'll see more powerful, but still noisy, machines solving specific problems in science and industry. By 2040, fault-tolerant quantum computers could emerge, capable of breaking encryption and designing revolutionary new materials and medicines. Everyday impacts, new drugs, efficient tech, advanced AI will become visible. In the second half of the century, we may see a quantum internet, connecting machines worldwide for secure communication and distributed computing. Quantum computers will move from labs to universities and corporations, following a path similar to classical computers. Progress depends on investment, collaboration, and breakthroughs in physics and engineering. The direction is clear. We're moving from classical limits to quantum possibilities. In 2025, we stand at a turning point, like the dawn of the digital age. Quantum computing is a fundamental shift, letting us harness the universe's deepest rules. Its impact will touch everyone. New medicines, efficient logistics, sustainable materials. This revolution will ripple through society, shaping the world for generations. Quantum computers will help us tackle science's greatest mysteries, from consciousness to the cosmos. The journey is just beginning, with immense promise and responsibility. Today's machines are the ancestors of a technology that will redefine. By embracing quantum science with wisdom and cooperation, we can unlock a healthier, more prosperous, and astonishing future.